So what I want to do today is give you guys an example of a function that's not Turing computable. So some of you might have heard of it already, especially those of you in course 6. But the whole thing is so beautiful that if you're like me, you'll like just going through it anyway. OK, so the function that we're going to show is not Turing computable is the halting function. And here's how it works. We are going to give the halting function two numbers. And it is going to deliver 1 as an output if the nth Turing machine halts an input k. And it's going to be 0 otherwise. So what do we mean by the nth Turing machine? Well, that is relative to some way of ordering Turing machines, such as the one I gestured to here. There are many, many ways of doing it. The nicest one that I know of is in the lecture notes. But I'm not going to do it today because it would take a long time. So here we have a function from pairs of natural numbers to natural numbers. And what we're going to do is we're going to show that this function is not Turing computable. So the way the proof is going to work is we're going to assume that the Turing function is computable. Sorry, the halting function is computable. So that means that we have a program. It might be very long, but it's finite. And it delivers that result. And once we have that program, then we know that we can use it as a subroutine to construct other programs. And we're going to see that if we indeed had it as a subroutine, then we could do impossible things. So it cannot be a subroutine. So it cannot be a program. So the halting function is not Turing computable. One way of imagining this is if it were computable, then you would have like this machine such that you can give it two numbers and it outputs a 0 or a 1, the halting function. And you could connect that machine to other machines to do weird things. And what we're going to see is that if you connect it to other machines in the right kind of way, then you would be able to produce something impossible. OK, so here is our impossible machine. I'm going to call it the evil machine. So the evil machine takes one input. So take input, which is a string of k ones. And then the first thing that it does is create a copy of that string right next to the original one with a blank in between. If we give the evil machine a sequence of 5 ones, it's going to start with the reader there, and then it's going to do some stuff. And after a while, it's going to end up with a second sequence of 5 ones. And we even know how to do it. I mean, it's a slight variation of something we did on Monday. OK, and then the second thing it's going to do, and this is the crucial step, is that it's going to deploy the program of the halting function as a subroutine. Because remember what the program of the halting function does. what you do is you give it two numbers, and it outputs a 1 or a 0, depending on whether the Turing machine corresponding to the first number will halt given the input specified by the second number. So what's going to happen is that when we apply the subroutine to this, it's going to be like asking the question, does the fifth Turing machine halt given input 5? So then what's going to happen after we do that? In fact, maybe I'll write all steps. Is that we're either going to get a 1 or a blank. We're going to get a 1 if kth Turing machine halts on input k, and we're going to get a blank otherwise. OK, and now comes the evil part. If you get a 1, then what our machine does is it goes on a never halting task. So for example, it just goes right forever. And we know how to do that too. And if you get a 0, what it does is halt. So in other words, it does the opposite of the output it got. If the output it got is the kth machine halts on input k, it never halts. And if it says that machine never halts, then it immediately halts. OK, so we have our evil machine program. And because our evil machine is, we're assuming, a Turing machine, it has its number in our canonical numbering. Let's say that it's the ETH number. So then consider the question of what happens when you input E to the evil Turing machine. And what's going to happen is that it's going to ask the question of whether the ETH Turing machine halts given input E. In other words, it's going to ask the question whether it itself halts given the input you actually gave it. If the answer is yes, it's never going to halt. If the answer is no, then it's going to halt immediately. So in other words, it's going to do the opposite of what the halting function says that it itself should do. And that's impossible. So there can be no halting machine.